welcome everyone to our virtual colloquium today. Masha's going to introduce our speaker and I'll pass it over to you.
I'm Maria Cheung, an assistant professor at CU Boulder, and I would like to introduce Mark Cheung. Mark, thank you so much for being able to join us, although virtually. We miss you. Mark Cheung is, who doesn't know Mark Cheung? Everybody knows Mark Cheung, especially in the solar field. But a few words, Mark Cheung is a senior staff physicist at Lockheed Martin Solar and Astrophysics Laboratory, LMSL, in Palo Alto, in California. He's the PI for the Atmospheric Imaging Assembly Instrument, AIA, on board of NASA Solar Dynamics Observatory, a big mission, a flagship mission on the Living with a Star program. Mark's interests lie at the intersection of magnetohydrodynamics, remote sensing, high-performance scientific computing, and machine learning. So very wide range of interests. He completed his graduate studies at the University of Göttingen and the Max Planck Institute for Solar Systems Research. He has many collaborators in Boulder, and he really misses his frequent visits here. And then last thing, Mark also received Karen Harvey Prize, and we're very glad to have him here. Please start, Mark.
Okay, so first of all, thanks for the introduction and the invitation, Masha and APS, for this opportunity to talk about some of the work we do in our group. Today, we're going to talk about the physics of solar and stellar flares, especially concentrating on how we can study them using extreme UV observations and radiative MHD simulations. And because this is a fairly broad audience, your department is very broad, I won't be able to delve into some of the details of the research, but feel free to reach out and ask, after the seminar, during the seminar, or afterwards. So these movies are from the Solar Dynamics Observatory, which we use a lot to study how the sun evolves, and several of the snippets that you see involve solar flares and eruptions. This happens to be Venus transiting the sun in 2012. This is a flare. Just in case you haven't seen movies of flares, this is how they look like in the extreme UV. Okay, all right, let me continue. So I said I'll start with basics, so let's go ahead. Solar Astronomy 101, just in case you don't know. Here are what I consider the most salient observational features about the sun. So in the last movie, you saw that it was rotating. It doesn't rotate as a solid body. The equator rotates faster than poles. It takes about a month or so, but it differentially rotates. The sun has sunspots, and the number of sunspots waxes and wanes with an 11-year cycle, and with a 22-year magnetic cycle if you look at the magnetic field. The magnetic fields actually pervade the entire sun. The sun is a panchromatic astrophysical object. What do I mean by that? So this is a spectrum of the sun from gamma rays all the way to the radio. And you see that there's a lot of orders of magnitudes spanned in wavelength on the x-axis, as well as in the brightness. So it peaks at around the visible, of course, but then you will find that there are X-rays, gamma rays, and radio. Now, we're going to be focusing on extreme UV, which is just basically the halfway region between the X-rays and the UV. You see that there's quite a lot of structure here. And we can learn a lot using the structure in this wavelength range. You can see also there are radio signals. In particular, when the sun is active, you have radio bursts. Okay, so it's a panchromatic astrophysical object. The hot corona of the sun consists of loops anchored at or near sunspots. When we compare images of the surface with the EUV images of the corona, that's an obvious thing we see. And then total eclipses are totally awesome. Partial eclipses less so. And I want you to know about 2 upcoming eclipses. There's the one in 2023, which is an annular eclipse if you go to the eclipse path. And then there's the total eclipse one in 2024. If you just stuck around Boulder or in Colorado, you'll see a partial eclipse in 2023. And if you went to the path of the annular solar eclipse, you will be able to see that there is a ring when the moon is almost covering the sun. And then you'll say to yourself, oh yeah, okay, that's not bad. And then the risk is that you will not make the effort to go to the total solar eclipse in 2024. And that would be a huge mistake, because if there's any take-home message, that is an annular eclipse is sort of boring. A total eclipse is totally awesome. So plan for that. All right. Let's go into the interior of the sun. We have a radiative core. We have a core that does fusion, and then there's a radiative zone. And then on top of that is the convection zone, where the energy is not carried by photons diffusing away, but mainly by flows convecting. And you have a lot of expertise with APS, who are the experts on studying the solar interior, including how the convections leads to the generation of magnetic fields. There's Yuri Tomere, Ben Brown, and Mark Rast. And then once we reach the photosphere, the density contrast between the bottom of the convection zone and the photosphere is about 1 million. So it's much more tenuous at the photosphere, at the surface. That's where we see most of the light that we see invisible. And there's the DKIST telescope that's going to revolutionize our view of the photosphere and the chromosphere immediately above, as well as also be able to see the corona. So at APS, Mark Rast is involved with leading that effort also. And of course, in terms of the corona, it's known to be hot, millions of Kelvin hot. So an expert in coronal heating and how solar and stellar winds are driven is Steve Kramer. It's really amazing how much expertise there is in APS regarding solar and stellar physics. So you're extremely lucky. The magnetic fields dominate the solar corona, and it almost is the driver of everything. Now, some science questions regarding solar flares. We're interested in how is it that you can build up the energy in the solar corona that allows you to have a sudden release that is enough to power flares and eruptions. And then once it's released, how does this energy get channeled and lead to the salient observational features, like, for example, flare ribbons? So Masha Kazachenko is one of the experts who are very interested in these problems. And then how do we learn about the temperature structure and evolution of coronal plasma, especially during flares, using multi-wavelength observations and detailed numerical modeling? And what lessons do we learn from studying solar flares that can be applied to other astrophysical systems, such as stellar flares, and vice versa? So for that, you have Adam, who just won the Karen Harvey Prize this year. So congratulations to him. So you can basically learn almost everything about the sun by just being in your department. And if I were to want to do a grad school now again, I probably would apply to the APS, but maybe I wouldn't be admitted because it's so competitive. Okay, so apart from flares, you also have coronal mass ejections. So sometimes it's thought that the magnetic field is so round up that you get twisted flux ropes, and they sort of wrap around magnetic field, and that magnetic flux rope gets pinched off, gets to escape the gravitational well of the sun into the heliosphere. Those are called coronal mass ejections. Not everything escapes the gravitational well. Sometimes the material can fall back down towards the surface. And these types of events have been used to as templates for example, stellar accretion events. For example, in this paper by Reale et al. So there's a lot of astrophysics we can do with the sun. The Solar Dynamics Observatory was launched so that we can have a better understanding of how the sun changes and how it affects our daily lives and technological civilization. It is a science mission, so the focus is to better understand the sun and all the science behind that. SDO has 3 instruments. There's the atmospheric imaging assembly, which gives you all these extreme ultraviolets and UV images. There's also a visible channel, although that doesn't look that great anymore because of some pinholes in the front filter. But for visible light images, you have the helioseismic and magnetic imager, which gives you continuum or quasi, let's say, white light images in spectral lines that allow us to measure the Doppler flows of the plasma at the surface and also the magnetic fields at the surface. And these Dopplergrams are used to do helioseismology, to probe the interior of the sun. EVE, the EUV variability experiment led out at LASP, provides this integrated EUV irradiance spectra at 1 angstrom resolution. So it has a lot of information about what spectral lines and what species are emitting. So this is in one slide all the types of data that SDO produces. There's of course higher level derived data, but in the middle panel you see EVE spectra at the UV and EUV wavelengths. Well, mainly here is the EUV. And then you get the HMI images, the Dopplergram here, magnetic field, and then the rest are AIA images here. Okay, so we can take a look at the spectrum in the EUV during a small flare. This is what EVE measures. EVE has the max A and the max B channels, and the max A channel is the one that persists here in this movie. The max B channel is the yellow that flashes in and out. So this is what max A covers. The dash marks are the central wavelengths of the AIA EUV bands, as well as the UV and the visible bands. This is another plot showing the bandwidth of the AIA channels. And you'll see that actually AIA channels are sufficiently broad in wavelength space that you don't just pick up one line, you pick up multiple lines. And these lines are due to ionized species emitting because they're formed at different temperatures. So each of the channels of AIA doesn't show just temperature, one single temperature. So we have to be a little bit careful about how we interpret the data. From EVE, what was a new discovery was that other than just the normal flares, there are some that are called flares that have a late phase. These late phase flares basically have other than the main sort of a peak of the flare emitting in X-rays and in some EUV lines, they also then have for an hour or two or a few an extended release of EUV emission. And it turns out that when flares have these late phases, this late phase can contribute on average to 40% of the energy of a flare. And so then that matters for your energetics. That should matter for the energetics of the thermosphere or ionosphere at Earth. So that's a big discovery. And Thomas is the PI for EVE. Again, it's a last mission. So you can learn all about that by talking with people like him or Frank. So I mentioned earlier that you have several lines in each of the AIA bands. It requires a physics model to examine what lines might be important in the band. So when people use Chianti, the atomic package, they can predict that, oh yeah, these might be the interesting lines. And each of these iron species, multiply ionized irons, are prevalent at different electron temperatures. So basically, AIA channels are sensitive to a range of temperatures. Keep that in mind. So other than flares, there's also coronal dimmings. In this plot here, in the let's see, let me show the cursor. In this brown, dark greenish bar, there's a so-called coronal dimming, and it appears in the iron 9 line. The emission in this line is actually below the pre-flare. That's called a coronal dimming. If you are able to image a coronal dimming, it might look something like this. So we're not talking about this big patch of dark here that's persistent. That's a coronal hole. That's typical of magnetic fields that reach out into the heliosphere and cause the fast solar wind. We're talking about a temporary dimming around a flare. What's really, really exciting about coronal dimmings is that they are often associated with eruptions. And in a recent study by Veronique et al., it's reported that when you have a coronal dimming detected, then it's quite a high likelihood that the flare was eruptive, meaning that there was actually a coronal mass ejection accompanying that flare. So flares typically cause huge enhancements in some of the hotter lines, but in some of the cooler coronal lines, like a mega Kelvin or less, you might see this dimming. So the idea is that if you see coronal dimmings in Eve, you see coronal dimmings on the sun, you could use these coronal dimmings on other stars to detect stellar CMEs. And Kevin France had a proposed mission, ESCAPE, which unfortunately isn't selected for this round of the astrophysics MEX, but I hope it gets revived because it would be a really exciting EUV mission to detect stellar CMEs. The images from the EUV images from AIA are used to calibrate some MHD models of the global corona. For example, the University of Michigan has the so-called AWESOME model, and they take the magnetic field at the surface as a boundary condition. They use some parameterized heating model, and then they produce these synthetic images of the time-relaxed state of the corona. And they compare visually sort of okay against AIA, and they can produce a hot corona and a solar wind. But there's a lot more to do to get everything quantitatively correct, especially regarding the wind. But mind you, these models are now being applied extensively to modeling space weather at other stars in exoplanets from stellar hosts. So given that it is a parameterized model of coronal heating, that quantitatively isn't right everywhere, and that's the quality of your magnetic field boundary condition from, say, Zeeman Doppler imaging is very different than the magnetograms that we get for the sun. I think we ought to be careful about how much quantitative conclusions we talk about space weather at other stars. There's a lot of work to do. There's a lot of interesting work applying to different systems like TRAPPIST. But from my point of view, one should take these with a grain of salt. EUV astronomy is not so well acquainted, or like, let's say, a lot of astronomers are not acquainted with doing astronomy with EUV because of extinction and because of sensitivity issues with past instruments. But actually, there's a lot of things you can do if you can see the EUV. So even in tidal disruption events, when stars are being torn apart by supermassive black holes, the modeling shows that the spectrum would peak at EUV wavelengths. Oh, if only you could see it without the extinction. And that's because whenever you have a megakelvin plasma, you're in the right regime where the emission lines give you are in the EUV, and you can learn a lot about the physics if only you could observe it. Okay, so what does AIA actually see? Once you use an atomic model to look at what lines contribute to a wavelength band, then if you look at the different wavelength bands, you find that, oh, they're all sensitive to different temperatures. So if you want to know temperature maps of the sun, of the solar corona with AIA, you need to solve an inverse problem. You basically have some linear system which is underdetermined, but if you use some compressed sensing scheme or other regularized inversion schemes, you can solve for how much plasma there is in terms of the line of sight integral of the electron density squared at different temperatures. And so you can get temperature maps that are like this is scanning in temperature space from about 500K to about 8 megakelvin. And these are the coronal loops above a flare productive active region. So you can really map the temperature structure of active regions. Once you solve for the so-called emission measure distribution using data like from AIA, you can then create mock images in X-rays. So lots of astronomers are more comfortable or familiar with X-ray astronomy. So this shows, the left column is an actual X-ray image from the Hinode emission of an active region. The middle column shows the synthetic X-ray images using the EUV data from AIA. So it reproduces the X-ray data pretty well. So that speaks volumes as to the diagnostic capabilities of using EUV. Okay, let's talk a little bit about models and observations versus observations. Of course, we can't have a full lecture on MHD, but I'm aware that not every student has taken an MHD class yet. Yeah, we talked about your curriculum at the Colloquium luncheon with the students. So here's the basics. MHD is essentially the principles of mass conservation, momentum conservation, energy conservation, and Faraday's law. And I like writing the fluid view because it's easy to visualize. So the density changes because of compression or not. The momentum changes because of surface forces and volume forces. The surface forces are the divergence of a tensor, stress tensor, and the form of that depends on the material properties that you assume in your system, but it also depends on the magnetic field, and that's the Lorentz force. There's energy conservation, but how the energy moves around depends on whether you have electrons that stream very quickly, whether you have radiation, and so on. And then you have the induction equation. And the form of the electric field and how it relates to the velocity and the magnetic field and possibly other quantities also depends on what you assume about the material properties. But the idea is that in the solar corona, it's electrically conducting, highly ionized, and so it's almost ideal most of the time. And then when you write it in the Lagrangian form, it's very easy to visualize what's happening to the magnetic field. When you have compression of the plasma, it strengthens the field. When you have expansion, it weakens it. And then when you have the projection of the velocity gradients onto the magnetic field, stretching of the field lines also strengthens the field. So that's the intuition that you could get. It's really a fluid picture. All right, so people apply these MHD models to flares. And this is a sort of standard view, is that you have magnetic field that is hanging in the corona, oppositely directed, and at some point, the oppositely directed magnetic field reconnects. And the reconnection, what happens is that the reconnection allows the magnetic field to change the topology. Once it has changed the topology, then the magnetic field lines can relax into a lower energy state. The reason they want to relax to a lower energy state is that in MHD, the magnetic field has magnetic pressure as well as magnetic tension. The magnetic tension wants to straighten out field lines. The magnetic pressure wants to sort of homogenize the magnetic field. So once you change the topology, you allow it to go into a new equilibrium, and it does so. And in doing so, it has a bunch of predicted and observed effects that come with it. That is a sign of the energy release. One model of this in 1998 shows that if you include the efficient transport of energy carried by electrons, but modeled as a thermal conduction along field lines, then the energy release from the relaxing field will then be dumped into the chromosphere, so just above the photosphere. That heats up the plasma. The plasma rises. It's called chromospheric evaporation, and then that chromospheric evaporation provides the bulk of the plasma that creates this increase in the EUV and in the X-rays. The model also predicts that as the magnetic field lines are retracting, it compresses the plasma, and it also leads to an enhancement of the density in the termination region. And it could be a plasmoid shock. So with AIA, you can then solve the temperature distribution. And let's say we have the temperature distribution, but we just do an emission measure weighted temperature. So an average temperature map. So this is for a flare that's happening at the limb. And so we're looking at this, but sideways, turned sideways 90 degrees. The red line is the average temperature along the dashed line, and the black solid line is the total emission measure. It's like it's a measure of the square of the electron density. So at the beginning of a flare, you see that there's an enhancement in the temperature and the emission measure. Okay. Further on, you get the enhancement grows. You also get an outflow towards the right that's away from the sun. And you see that in the temperature map, it's sort of a big arch that is sort of homogeneous. The reason is quite homogeneous, even though the density structure doesn't increase so fast yet. It's because of the efficient thermal conduction. Okay, so you can continue. The more magnetic fields are reconnected and piling up. Eventually, you get orders of magnitude increase in the emission measure, and the peak of your temperature, of the temperature of your plasma, is propagating higher and higher up. So this is what we observe with AIA. Okay, another way to visualize that is that, again, we have the temperature map, but we also have contours of the emission measure. So dash contours show enhancements. And you see that near the beginning of the flare, you already get a compression near the top. That is the blob that is predicted from that 2D model. You also get these enhancements at the legs. Those are the humps, the chromospheric evaporation, and the chromospheric evaporation grows, and the material coming from the blob also grows towards, and then you get a even stronger enhancement of density as more and more material is evaporated from the chromosphere. More recent MHD simulations, including this effects by Takasawa et al., looked at the dependence on the efficiency of the thermal conduction along the magnetic field lines. Again, this is carried by the electrons. And the left column is for when you don't have any thermal conduction. The right is when you have a stronger thermal conduction. And the top is the temperature, middle is the density, and the bottom row is the vertical component of the velocity. And in these three models, you can see that the temperature and the density structures are quite different, as well as the velocity structures. And what he reports is that when you have higher thermal conduction, you get a stronger compression. The density enhancement is greater when you have thermal conduction. The easy way to think about this is that when you're thermal conduction, you can, when you are compressing the plasma, yes, the temperature does go up and the pressure, the gas pressure does go up, but it doesn't go up as high because the energy is able to be conducted away. So the plasma is more compressible. So that's why you get a higher density enhancement here. And because you have thermal conduction, the energy is carried more efficiently down to the chromosphere, and that brings more mass up. So building on this type of work where people have done sort of simplified setups for flare loops, we now have a simulation of a solar flare in a full cycle, meaning we start with some magnetic field that is anchored in the convection zone. We have the emergence of magnetic field, which introduces stresses and allows the energy to build up in the corona. We get the twisting of the field, and then we get the destabilization and allow the magnetic field to release rapidly and release energy rapidly, so that we get observables that are qualitatively like what we observe in flares. This is a group effort, and I hope you can hear the music. This video explains it much better than I can say live, so please enjoy.
What just happened? Let's take a look at the life cycle of a solar flare. This is our sun. Magnetic loops above sunspots trap and heat plasma up to a few million kelvins. When magnetic fields are pressed together, they can snap and form new loops, a process called magnetic reconnection. Magnetic energy is released rapidly, heating plasma in the sun's atmosphere to much hotter temperatures. At the same time, magnetic forces eject plasma away from the sun. Like metallic rods, coronal loops are efficient conductors of heat. Energy conducted to the base of the corona launches fountains of hot plasma into magnetic loops. The magnetic loops, now filled with hot plasma, emit profuse quantities of X-rays and extreme ultraviolet radiation. Eventually, the solar flare subsides, the hot plasma clouds cool, condense, and fall. This is called coronal rain. Let's see it again.
So kudos to Mark DeRosa for narrating this, and to Georgios Chinzoglu. He is our researcher who composed the music himself. Right, so I guess things going on in the chat. Marsha and Lauren, let me know if there are questions that I should answer imminently. Otherwise, I'll continue.
I think we can hold off on them till the end.
Okay. So with a simulation like that. So what happens actually is that, let me briefly describe. So we have in our MHD model a pair of sunspots that are pre-existing, and then we emerge a dipole. So a twisted field that is coming up next to this red sunspots. And what happens is that the shear flows and the twisted field emerging here creates a coronal flux rope, which is bounded by the overlying field from the red sunspot. Eventually, though, the overlying field also reconnects, and the strapping part of it removes, so that this flux rope can leave, and then you get the synthetic X-rays that look like this for the short and long wavelength bands of XRS. So you get the quick rise and the slower decay. And the energy released here is only about 5 by 10 to the 30 ergs, and it's about a C4 flare. One other thing we can look at is the spectrum of the Bremsstrahlung. And if you just assume, because it is a thermal MHD model, if you assume just thermal Bremsstrahlung, it turns out that because there are components of the plasma at super hot temperatures, even beyond 100 megakelvin, just using that and synthesizing thermal Bremsstrahlung would give you a spectrum that looks like a power law, which often when people look at power laws in X-ray spectra of solar flares, it is often interpreted that these are evidence of particle acceleration. Here, we're not dealing with the details of the particle acceleration, just from the energy conservation, when magnetic fields relax and you get some pockets that are very hot, and the thermal Bremsstrahlung would just be at the high energies and give you this power law spectrum. So in this case, the power law spectrum, the synthesized power law like spectrum, is a reflection of the multi-thermal nature of the plasma in the flare. That was a sort of data-inspired simulation of a flare with as much nuts and bolts as we can afford to introduce. What we want is to be able to use the magnetic fields that are measured by SDO, like this here. It's a nice vector magnetogram visualization by KG from the HMI group. We want to use those to drive how the magnetic field looks like. And so there's a project called CGEM. I've been working with the Berkeley folks and the Stanford folks, and Marsha has been a central part of this. She has the methods to use the sequences of the vector magnetograms to look at how you can get the electric fields that you use as a boundary condition to drive the evolution of the magnetic field above the photosphere. And I think Sudong is online. He is also very much involved. Yes, and I think this type of work carries on. And the goal is to develop data-driven MHD simulations, and many groups are doing that. But the level of how you deal with the boundary data to do the driving is still an active field of research. Finally, I want to talk very briefly about a new mission that is proposed, the Multi-slit Solar Explorer. So from what I said, it seems like there's quite a bit that we know about flares. Flares have been studied for a long time, eruptions for a long time. We have such high resolution, high cadence observations from AIA. So why do we still want to have another mission? Well, MUSE is a spectrograph, but a special type of spectrograph. And MUSE has 3 science goals: to determine which mechanisms heat the solar corona and drive the solar wind, to understand the origin and evolution of the unstable solar atmosphere, and to investigate fundamental physical processes. And I can't cover everything here. We have 2 papers listed here in archive that are in press that cover all this. But the problem is that imaging instruments have limited diagnostics. Yes, we can do DEM inversions, but we don't have like flows. We don't have Doppler flows. Single slit spectrographs, which usually allow you to get the Doppler flows, miss the big picture because they're very slow. You have to scan slowly. And even with EUVST, with high throughput, because you have high resolution with EUVST, you still have to take a long time to scan. And then for others, low resolution and low cadence observations meet the fine scale structuring. So MUSE tackles all that. The reason we want to go to sub-arcsecond resolution, so AIA is on the order of 1 or so arcseconds. The reason we want to go to higher resolution is that there's a lot of strands that are detected in sounding rocket experiments like HI-C and UV telescopes like IRIS, and also Hinode, showing that there's a lot of structuring going on at those scales. And also there's a special scale in the intergranular lanes in the convection that is creating these structures. So we want to go to those resolutions with MUSE. It's undergoing review. Hopefully it'll be selected, let's hope, in March when NASA announces which mission they select. The really special thing about MUSE is that as opposed to a single slit instrument, which scans a region like, for example, like EUVST like this, MUSE has 37 slits, and all these slits are taking spectra simultaneously. So it's 2 to 3 orders of magnitude faster when scanning a region. So you're not blind to the dynamics. You're actually doing imaging spectroscopy at the speed of the corona. One of the unknowns about solar eruptions is what is the trigger? Is it a reconnection in the corona above a flux robe? Is it a reconnection below? Is it a reconnection that causes a sheared arcade to become a flux robe as it erupts? Because we don't have the scanning capability to catch a lot of these events, we don't know. But with the 37 slits, we'll be able to show it. We'll be able to detect the bidirectional flows that are the reconnection triggers. We can do maps of eruptions like these in the iron 15 and iron 21 lines at high cadence, at like even 10-second, 20-second cadence, depending on the step size, or even 1 second cadence, but with 37 slits there, we'll be able to find the Doppler flows relating to how the plasma is evolving in the eruption and in the downflows in the ribbon. And then regarding reconnection, there's a lot of models, theoretical models on plasmoid mediated reconnection. So there's the plasmoid instability, which is predicted to happen when you have Lundquist numbers above a few thousand or so. And they predict multi-scale plasmoids. There's some evidence of some plasmoids in AIA data, but we don't really have multi-scale plasmoids, and we don't see them really merging and seeing all the dynamics, and MUSE will be able to capture them if they exist. MUSE will also be able to capture fine-scale structures in a termination shock. If you have multiple interacting plasmoid shocks in the termination region, as predicted by these papers, you would also be able to detect them. And now finally, the next generation solar physics mission is a concept developed by solar physics experts designated by NASA, ESA, and JAXA. And following 70 plus white paper submissions, they prioritize the mission with the following suites of observing capabilities. So they have a high resolution coronal transition region spectrograph. There's a high resolution chromospheric photospheric magnetograph spectrograph. So DQ satisfies that, EUVST satisfies the other, but there's no coronal imager, high resolution coronal imager at the moment. EUVST does not have context imaging in coronal lines. And so MUSE would be able to fill that gap. Of course, it is also a spectrograph, so it fills part of the box on the left also. And with EUVST, MUSE, DKIS, and other ground-based observatories will be able to execute NGSPM science. Okay, I'm going to stop speaking. Of everything that I talked about, the most important take-home message is go to the solar eclipse, the total one. You will not be disappointed. And then there's a bunch of other stuff, but I think I will stop there. Okay.
Perfect. Thanks so much. That was wonderful. So we can move to Q&A, and there are some, compliments in the chat about the video and the music. There are also 2 questions in the chat, so maybe we can start with those, and then if other people want to raise their hand and ask questions or write them in the chat, feel free. So Ward Howard had a comment or a question in there. I don't know if you're on and would like to read it yourself. Go ahead.
Sure, thank you. First of all, that was an amazing colloquium. I felt like I learned so much, it's going to take me time to even digest it all. I was wondering about 2 things in particular. One was comparing 20-second cadence observations by MUSE with stellar flare observations, also taken at 20-second cadence, to look for similarities or differences. If that might help direct that motivation. And also talking about the coronal dimmings, would these coronal dimmings likely to be related to type 4 bursts that we expect to see from M-dwarfs that do not see?
So what? I think I heard some of the words, but there was a lot of feedback. So you were asking, thanks for the compliment. You were asking about the 20-second cadence observations with MUSE and 20-second observations of tests. Let's see, what can be learned? I'm just going to read the question you posted on the chat and take that as the same as your verbal question, okay?
Yeah, my speakers are acting up right now.
Yeah. So MUSE is observing in the EUV. It's using EUV line, so it's really strictly looking at the coronal plasma. But what we can do is that when we have coordinated observations between DKIST, for example, and EUVST with MUSE, and that's a central part of the proposed MUSE science investigation, is that we'll be able to learn about the full structure of solar flares, from the connection from the photosphere to the corona. We'll be able to learn about the timing clearly, about some what's causing what. We'll be able to look at certain aspects of white light flares that we can detect with DKIST, and look at their relationship with the EUV, and I think that is an important problem. The typical way that stellar flare, super flare observations are interpreted is that you get a bump in the sort of wide band integrated lights from Kepler and TESS. And I think you often would find that it's like you assume a black body at a certain temperature, and then you convert that into an energy. There is work by Heinzel and Shibata, for example, actually that looks at flares that people observe in HMI of the limb. So in white light, HMI also saw some limb flares, and they report that's the major contribution is actually not from the foot points, but actually from the loops of that strong flare. And that's, I think, Paschen continuum. When you take that into account, how does it actually affect the estimates of the flare, of a stellar flare? It might just be a factor of a few and not orders of magnitude, but that problem isn't really addressed as far as I know. And it would be very nice if people took those details into account before they apply wholesale interpretations of Kepler and TESS observations. Yeah.
Great, thanks. Let's take one more question from the chat. Marcel, I don't know if you're on and want to ask yours or if it still applies.
Yeah, just very, very briefly. First of all, Mark, thank you for the great presentation, and the video was amazing as well. Just when you were talking about this multi-slit imaging, I was just curious about how it will actually improve our observational capabilities. I know you explained it, and it went a little fast for me. So if you could just like elaborate on that a little bit more, I would be interested to hear that. Yeah. Yeah.
Okay. So the problem with single slit instruments is that when we want to scan over a region that is like a active region scale, typically it would take several minutes at least. But because the corona is very fast, especially during eruptions and flares, the corona changes a lot within tens of seconds and certainly within minutes. So when you use a single slit instrument, you simply miss a lot of the action. If you had some context imaging, you could sort of guess what's happening, but then you're back to like you might as well just use AIA. But the other part is that because it's a significantly higher resolution than AIA, you'll be able to see much finer structure and find the plasmoids, for example, if they exist, find the interacting plasmoid shocks if they exist. You would also, because you now have a almost simultaneous spatial temporal coverage, you can then use the correlations, the spatial temporal correlations that you measure in the whole spectral raster to constrain different models or to test different models. Whereas before that, we just didn't have the available data. So for example, with Hinode ice, it took a long time to catch some of those flare ribbons or the current sheets. And this, you can probably count it with a single hand, how many times you're able to catch those type of events with a single slit instrument. But you won't miss it with MUSE.
Thank you.
Great, thanks. Yuda, do you want to ask a question? Comment?
Yeah, can you hear me?
Yes, not so
Yeah,
yes.
yeah. Thank you for interesting talk. And actually, I have several questions that I ask one. So in your simulations in a Nature Astronomy paper, you suggested a non-thermal shape of coronal X-ray spectra are reproduced from your simulation, right?
Yes.
And do you have any expectations for our understanding of non-thermal component? For example, how affected in a previous observation or from LESI or other instruments? How do you think?
Yeah, thanks for your question. So first of all, there is no doubt that there are energetic particles that are not just that there are non-thermal effects in the acceleration of particles, and that you need energetic particles to explain, for example, the hard X-ray footpoint sources. So if you just did the thermal Bremsstrahlung like we did, then you don't reproduce the hard X-ray sources at the foot points. We could do that if we decided that we assumed a fraction of the conducted flux were in terms of energetic particles and used a, I don't know, thick target model, then we can reproduce that. But we just didn't want to make that assumption. We knew it could be done, but we just didn't want that to be part of the paper. So there's definitely evidence for energetic particles. The question is, in terms of the overall energetics of a flare, in terms of the overall energy transport, how important really are the non-thermal particles? I think the reason that the non-thermal picture, other than the hard X-ray sources, is so pervasive in the flare community has to do with that when you look at the X-ray spectra, you can't fit it with a single thermal source. So what's the natural thing to do? Okay, you fit it with power law, and then you can ascribe to it that, oh, this is due to non-thermal particles. But actually, you can also fit a multi-thermal distribution, and you can fit that spectrum pretty well. So at some point, I feel the term power law and energetic particles, non-thermal energetic particles, became synonymous. I don't think that necessarily needs to be so.
Okay, thank you.
Thanks. Let's move on to Valentine and we can go back to you if there's time.
So hi, Mark. This was a
Hi,
great
Valentine.
talk. So in the context of the explaining the MUSE mission, you mentioned that one of the things we need to understand better is how these flux ropes are formed, and you mentioned several possibilities. But then in the context of the fantastic video, you also mentioned that in the simulation, you do have a flux rope.
Yeah.
So my question is, how was the flux rope formed in the simulation?
Oh, yeah. So thanks. In the simulation, the flux rope is formed by the emergence of twisted field in that parasitic dipole. And then, so first of all, the coronal flux ropes don't emerge from the convection zone into the corona intact, and that's how they are formed. It's never that simple. And the reason it's never that simple is that imagine you have a flux rope in the convection zone at densities below the convection zone, and you just bodily transport it up to the corona. What happens is that because the coronal densities are so much lower, all that mass has to be able to fall, but then it has nowhere to fall because you have these convex field lines, or it has to be able to disappear somewhere, because the corona is about 1 million times less dense than the photosphere even. So the only way for coronal flux ropes to form is if you have already reconnection. There's a lot of reconnection at the photosphere and in perhaps the chromosphere that allows you to take the mass out, and you can maybe reform a flux rope. So that's what happens in this simulation. You get a coronal flux rope that's reformed. It's just one example of something that can form like that. It doesn't mean that that's how the majority of regions on the sun do this. And that's what we're missing. We're missing the data to tell us whether it's mainly just shear arcades that suddenly become flux ropes, or whether it's a pre-existing flux ropes that's been hovering around for many alphane crossing times. We can have the data to do it with MUSE, but we simply don't have the data right now to constrain.
Yeah, that's good. Thank you.
Great. Tetsu?
Oh, yeah, thank you having time for me. And yeah, thanks, Mark. Good talk. Yeah, I have a similar question with Yuta about non-thermal effect, and that's good idea. Multi-thermal component produce X-rays power spectra. And my question is, in your simulation, is there some MHD scale phenomena implying particle acceleration other than reconnection? For example, shocks or compressing plasmoid or collapsing plasmoid. If there is no, it strongly supports your idea. That's my opinion.
No, there are shocks in the simulation. So there's all that type of a usual MHD scale phenomena. So let's say when I say that there is no particle acceleration, there is no treatment of the particle acceleration that is necessarily motivated by certain understanding of the microphysics. What the simulation does is that it does conserve energy. So when the magnetic field relaxes, the work done by the magnetic field has to go somewhere. It tends to accelerate flows, and then you can have compression, and you might get a dissipation. But the decrease in the magnetic field energy goes somewhere into kinetic and then eventually thermal. So even though there is no particle acceleration mechanism, the fact that the Lorentz force does work, it will compress certain regions so that they have higher internal energy, and the higher internal energy is associated with a higher average energy per particle. So that's how the acceleration occurs, but it's not like an isotropic. That's not what the model treats. So that's why you get these super hot plasma pockets in the simulation. So that's the limit of the simulation, and I think there's there is the opportunity to, let's say, start with some intermediate snapshot of the flare loops and do some 1D loop models that do treat the kinetic physics, or even do a particle in cell model if we can manage to see how that affects matters for the bulk energetics or for certain observables. It's certainly important for certain observables. We don't know how important it is for the bulk energetics.
Yeah, thank you.
Great, thanks. We are at time, so I think we can all thank Mark again for the wonderful colloquium. And I don't know if people do have more questions or comments. I imagine you can feel free to reach out. Yeah,
thank you very much for the opportunity, and nice to see so many people on, including many I've known for a long time. Miss you all.
Thanks again, Mark. We really like your